we want to look at a little bit more on functions before we start looking at actual functions. Remember, we had domain and range on functions, and these are kind of the x coordinates, and the range were the y coordinates. And so there's kind of this natural underlying graph that goes with functions. And so in calculus, it's going to be very graph heavy. I mean, there's a way to look at calculus with just the symbols and then with all the geometry and the graphs. So we want to look at that a little bit here. So every x and y coordinate that we generate, we plot, and we can draw the graph of the function. So I could start with the graph and ask you things about the function. So for example, here we have this definition of a vertical line test. So if I just give you a graph and I want to know if that graph represents a function, then here's how you check that. You take a vertical line, and if that vertical line doesn't intersect the graph more than once, then that turns out to be the graph of a function. So here's an example. That parabola we had turns out to be a function because if I take vertical lines and start drawing them, no vertical line that I draw is going to intersect that graph more than once. This one intersects. They all just intersected in one place. As opposed to, say, something like this one where I draw it. Let me make it a different color. So I've got this graph coming through here. If I start drawing vertical lines, you can see, for example, that vertical line, it's intersecting the graph in 4 different places. It's intersecting the graph there, 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 and there. So this isn't a function. And the reason why is because there's one x right here, that x that I'm plugging in, and notice it's giving me 4 different y coordinates. y1, y2, y3, and then up here there's a y coordinate. So 1x is breaking up and giving me 4 different y's. That's not a function, right? That was what we said. What violates our definition is if ever our x splits up and gives me more options than one. I want only one option to call it a function. So that's why the vertical line test, if it fails it, that's why it's not a function. So here's an example. Let's take this graph. Let me scroll down just a little, get some room. All right, so I've got this graph, and I want to know, first of all, is this the graph of a function? Well, if I start imagining vertical lines passing through this, it's pretty easy to see for most of these places, yeah, it looks fine. Only place might be right here at 1, but the notation here, the solid dot means include that point, the open dot means don't include that one. So it was strategically drawn so that when I draw this vertical line, it's hitting the bottom of this, but not the graph itself, just getting that open spot and then hitting where it's solid. So it is a function. The fact that we don't have things defined out here, that's fine. That's what happens with a lot of our functions. The domain doesn't have to be all values. And so given that it's a function, first question would be, what is the domain? And remember, the domain are the input values, the x coordinates. So I look at my graph and I determine which x coordinates are included. So certainly -3 is included. And as I move over here to the right, all of these are included because there's a point on the graph that I've graphed, that I've plotted, meaning that x coordinate's been included. Oh, right here, that one's not included, but it's included down here. So there's an x coordinate all the way until I reach 2. Once I get past 2, no longer any graph, meaning no longer any x coordinates, no more domain elements. The range is looking at the y coordinates. So I can kind of look through here. I can see, well, I've got y coordinates all the way here. And then all of a sudden there's a gap. No y coordinates are included for these y's. But then they start up again at -1. So the way I have to write this is usually when you just have a single value, you put it in braces. So -1 is in the range. Then you have to skip up here using the union symbol, starting at 0. That's included. And you go all the way up until you reach 2. And then there's nothing beyond that, nothing else down below. So that's my range values. So again, it's a snapshot of which x's are being plugged in and what are the y's that are then coming out. But I can also do things like I can ask, what is f of -1? Well, you're plugging in this x value and you go up to the graph and you see what the y coordinate was that went with it. Well, that y coordinate was 2, right? Because I can see that that particular point has coordinates -1, 2. I could ask something like, for what value will I get 1? So this time I don't know the x. And so I go over here where y is 1. I go across, okay, well, there was an x right there. And I go across over here and I can see there's another x. And that's fine. 2 x's can give me the same y. I just can't have one x give me 2 different y's. So let's say this, we're approximating. I'd say it looks like about a negative, just maybe 2.4, not quite 2.5. And then also over here, maybe about positive 0.8. You can only estimate from the graph unless you've got some grid behind it or something. Anyway, I can ask things like that. I can ask about increasing, decreasing. That's something we'll do later. Increasing means exactly what you think, means the graph is rising. It's here. And we designate that by the interval. It's increasing on the interval from -3. And a lot of times we don't put the endpoints just so there's no ambiguity there, because is it increasing or is it not here at the other endpoint? So it looks like maybe -1.5. Somewhere in that region it's increasing, and that's it. Nowhere else is it rising. Then it's constant, meaning it doesn't rise or fall. Then it falls, which is where it's decreasing. That's decreasing from, looks like where about 1/2 until I reach 1. It's decreasing, and then again it's constant after that. So we can ask things about increasing, decreasing. So there, like I said, there's this nice geometric component to functions, and there's an algebraic component. Another geometric component is on symmetry. So let's scroll down. Symmetry. There's symmetry all over in mathematics. Usually what you do when you have something that involves symmetry is you use it as a shortcut. You won't see that in what we're about to do, but well, I'll show you one thing where we can use a shortcut. So with functions, we have a couple of types of symmetry that we often look for. That is, either the function have an even symmetry or an odd symmetry. This is what it means to have even symmetry. If your function satisfies that, it's even. An even function has even symmetry. And if it's odd, it satisfies that. So let's go back over and see what that means. So let's read what this is saying. It's saying if I plug in an x and its opposite, right? That's what's happening here. I'm plugging in an x and its opposite. So here's my xy coordinate system. So if I'm plugging in that one and that one, you see that it's saying the outputs are going to be the same. So if this output's here, so is that one. There's my shortcut. I evaluated 2 points by plugging in 1 if I know the function is even. So this is the even symmetry. And so suppose I plug in this one and it's opposite. If I know this one's down here, then this one's got to be down here. And so the shortcut is, whatever the graph is over here, I have to have a mirror image of the graph over here. Because whatever I plug in, I got to have the same thing on this side, same y coordinate. So that's the symmetry. It's symmetric with respect to the y-axis, is what we often say about even symmetry. Symmetric with respect to the y-axis, which means if I take this half and fold it over the y-axis, it'll land perfectly on the other half. So it's got a nice symmetric look to it. For the odd symmetry, here's what it's saying. This time when I plug in a number and its opposite, I get outputs that have opposite signs. So again, looking here, if I plug in this number and its opposite, and this one's here, then this time I get not the same y-coordinate, but the opposite y-coordinate. If I plug in a number and its opposite, this one's down here, then this one's got to be up there. And so this is often said to be symmetric about the origin, because if I connect those with a line, that line always passes through the origin if you've drawn it right. So every point on these graphs, so if I have a graph looking something like this, turns out it has to go through the origin. Trying to make it look the same. No matter which points I connect that are on opposite sides of each other, it'll go through the origin perfectly. So that's called symmetric about the origin. And the way to think about that is if I fold this half over to the other side and then fold it over the x-axis as well, then it will land on the other half. So it's kind of a double folding. You have to fold it over and fold it over again, and it'll land on the other half. So that's our symmetry. So here's shortcut. If I tell you I have an even function and here's part of the graph, then what's the rest of the graph look like? Well, if it's even, it's got to look like this. It's got to be a mirror image of itself. It wasn't very good, but anyway, it's a mirror image. I just try to draw this on this side. And if it's odd, well, it has to go through 0. Then you draw one that's symmetric through the origin. So that's our shortcut of drawing graphs, but we use it in other ways as well. Functions that are odd and even turn out to be even-powered functions, end up being even functions. They're always symmetric. This one, remember, was a parabola. We looked at that on one of the videos before. You can see that it's nice and symmetric. The odd-powered functions are all odd. That one turns out it's going to be odd. Cosine turns out to be even. Sine turns out to be odd. Not every function is odd or even, but many functions are. But it's something that's got a kind of a geometric feel for it. We'll kind of keep an eye out. There's an algebraic definition, but again, there's this geometric underlying definition. So we'll do that a lot. We'll give you the algebra, the formulas, and then we'll look at the geometry, the graphing.